Okay, hi everyone. Let's get started. My great pleasure to introduce Professor Martin Wainwright. Martin is a professor in ECS and mathematics at MIT. He joined MIT in 2022 after spending 20 years in statistics and ECS at UC Berkeley. Martin is broadly interested in statistics, machine learning, information theory, and optimization. He has received many awards, including the COPS President's Award from the Joint Statistical Societies, the David Blackbird Award from the Institute of Mathematical Statistics, a section lecturer from the International Congress of Mathematicians, and the Sloan Foundation Fellowships. He has co-authored several books, including on graphical models, sparse statistical models, and high-dimensional statistics. We are very excited to have Martin today. Thank you so much for accepting our invitation. The floor is yours.
Yeah, it should be on. Yeah. All right. Thanks, Baharan, for the kind introduction, and thanks for the invitation to be here. Feels like we're still collectively recovering a little bit from COVID, getting back to in-person things. I always enjoy in-person things, talking to people here, hearing about what kind of research they're doing, what kind of problems they're working on. These kinds of things to me are part of what makes academia a lot of fun to be in. So I'm going to talk about reinforcement learning, and in particular the data-hungry nature of reinforcement learning. I'll be talking about a couple of pieces of work joint with different people, so I'll acknowledge those people when I talk about the particular work. Okay, so what's the broad motivation? Basically, life is a sequence of uncertain decisions. This time of year, I spend a lot of time talking to people on the job market, making decisions about jobs, or grad students deciding where to go for grad school. And these are sort of canonical, uncertain decisions. You're trying to make an optimal decision, so you have an action. We'll use A for actions throughout this talk. You have some notion of state. We'll use X for state throughout the talk. And what's key, unlike just going to grad school, is that there's typically a sequence of decisions that we'd like to make over time. Okay? And they're uncertain. There's probability. We don't know exactly what's going to happen in the future. Okay, so the basic formalization of this is the Markov decision process. Sort of historically, it's very old, goes back to literature in the control theory due to people like Kalman in the 60s, Bellman, of course. David Blackwell, a former colleague of mine at Berkeley in statistics, actually did a lot of work on Markov decision processes. And then a beautiful book by Bertsakis and Tsitsiklis from the 90s, and Sutton and Bardo. So it's a very rich and active area. I think one of the reasons it's been so influential is that the model at some level is pretty simple, but it models such a wide range of applications. Some of these applications are currently very hot, things like LLMs. But others, we've had so much success that we don't talk about it anymore. So things like aeronautics, every time you get in an aircraft control, things from Markov decision processes and control theory are in operation. Other things actually that are interesting in nuclear fusion, people are trying to use Markov decision processes to actually shape the plasmas using magnetic fields to try and build good fusion systems. So that's quite topical, quite exciting. So I personally find it very interesting. I'm sort of mathematically inclined, as you'll see, but I'm interested in mathematics that's sort of broadly relevant. I'm interested in models or procedures that can be applied to a wide range of domains. And so this certainly fits that particular, those criteria. Okay, so in this talk, what is reinforcement learning? Reinforcement learning will just be data-driven methods for learning how to act. If you want to make decisions in an online way, you make decisions according to what's called a policy. And when you use data to do that, we'll call those methods reinforcement learning. There's reasons from neuroscience that people call it reinforcement, but essentially it's just data-driven ways for learning how to act. What's sort of interesting here?
Over there.
Why is what?
If this is just data-driven for learning policies, why it's not enforcement learning? Rather, what DRE means, what Where is the re here?
The re comes, I guess, from the neuroscience thing that one repeatedly would do this and get enforcement repeatedly in the same direction. Frankly, I wouldn't read too much into the reinforcement per se. It's just language that's been adopted. I would say the distinction between dynamic programming, there you know the models, there's no data. You talk about Bellman updates. Here, somehow, the data is quite central. I personally think the most interesting thing is the hybrid between the two, partially data-driven, partly modeling driven. Happy to take questions, comments, anytime. Okay, so what's going on? It's kind of a strange state of affairs. There's really been tremendous advances in applied reinforcement learning, lots of pretty dramatic successes. But at some level, the theory has lagged very, very far behind. And I don't think this is just dissatisfying because theory should meet practice. I think this is really impairing how we could deploy these things in the world. If we don't understand them in sort of safety critical applications, it's dangerous. It's something that we don't want to do. So what are the positive features here? Positive features here are basically empirical success. People have, using large data sets, quite often neural networks, people have solved very large-scale problems. And really the advances have been quite surprising. At some level, it's interesting because the algorithms behave far better than you would ever expect from any kind of theoretical analysis. That's not because the theory is wrong. It's because the world has structure that the existing theory is not accounting for. On the negative side, what are the challenges here? Anybody who's ever tried to implement these methods in practice can tell you they're incredibly data hungry. They need a lot of data. And that may be a problem or may not be a problem, and I'll sort of explain why I think it's going to become an increasing problem. The other thing is there's a lot of instability, failure modes, lack of robustness, and this is really important if you think about using things, RL to make decisions in an online way for self-driving cars, for medical treatments, sequential design of medical treatments. There's lives that can be lost if you make incorrect decisions or don't understand the behavior of your system. So what I'm broadly interested in is sort of research in my group, not my group, but more broadly, theory that is theory, it's rigorous, but it connects with applications and explains and perhaps informs, guides, suggests directions for empirical work. Okay, so let me give you a little vignette just to be concrete. So this is sort of one of the original successes, big successes of reinforcement learning, a little bit old now, was AlphaGo Zero. So it's not purely reinforcement learning, it's actually competitive game playing. It certainly involved a healthy dose of reinforcement learning, a lot of clever search routines, things that are called Monte Carlo tree search and so on. But it's essentially a system that, of course, defeated the best Go player in the world, pretty dramatically, not even vaguely close. Okay, and Satinder Singh, he's done great work in RL, said one of the biggest advances in terms of applications for the field of RL thus far. And so that's certainly undeniable. And since then, these kinds of big hits have discontinued. We have protein folding. We have all sorts of things that have somehow succumbed to RL and big data. Now, I wear multiple hats, partly a computer scientist, partly an applied mathematician, partly a statistician. So you might think, okay, I'm fine, just use more data. But statisticians don't really think that way. Statisticians, because of their training, are often very sensitive to the cost of collecting data. And there are many applications, I've talked to many people here in the CS department today, where actually collecting data is very, very expensive, right? You might have to run a simulation, that might take an hour, it might take a day. So it's useful to sort of step back. How much data did they actually use in this initial version of AlphaGo? To be clear, these numbers, I'm sure, have been improved, but it's useful to do a little calculation. So AlphaGo used roughly 30 million games of training. The typical Go game has something like 200 moves per game, roughly. So if you compute, say a human were to do this, and let's say they spend 20 seconds per move. That's a very fast human player. How long would they have been playing for? They would have been playing roughly 24 hours a day, 7 days a week for 4,000 years. Okay, so Stonehenge, on the right there was built in 2000 BC. Of course, the computers aren't doing that because they're playing much faster and they're parallelized. There's millions of GPUs, so this is a serial computation. But I really think data efficiency is very important. It sort of brings in questions, what is the meaning of intelligence? Is it intelligence to learn something after a huge sample size? I have 3 children who speak 2 languages, and I can tell you they learn languages and new concepts very efficiently from small sample sizes. So I think one has to sort of think carefully about what is the meaning of this thing that's been created. More broadly, there's a very interesting paper by David Donahoe. He's a statistician and a mathematician. It's an archive preprint that he has titled provocatively, Data Science at the Singularity. He's partly making fun of AI, where people talk about the singularity. He's questioning that a little bit. But what he points to, he makes a number of, I think, quite thought-provoking observations. But one thing he points to is some work by DeepMind. That's what I'm showing you here. This is a plot that's studying sort of the resource efficiency of training various kinds of deep nets. On the x-axis, you have flops. If your model size is fixed, then flops is actually roughly proportional to how many samples you're collecting. So that's a measure of sample efficiency. And on the y-axis, you have training loss. Okay, so what's notable here is if these are both on a logarithmic scale, but if you sort of look at how much extra data did it require to reduce the loss by, 66%. It required orders of magnitude data, something like 10 to the 19 up to 10 to the 21 or 10 to the 22. Okay, this is not data efficiency. And Donahoe summarizes it like this. To be clear, Donahoe's been doing data science for 40 years. So he has some experience. He said, this is a breathtakingly bad exchange rate. He's talking about the rate at which models are improving, in this case with increased sample size. Its behavior is bad as I've ever seen documented in empirical work. Okay? So that's something we need to keep in mind. And he makes the point that this cannot continue. Okay? What he means by the brutal scaling is what we've been doing over the past 10 years is basically saying, throw more data at the problem, throw more compute at the problem, throw more parameters at the problem, and just scale, scale, scale. And that's been extraordinarily successful, but that can't continue. We're running out of data. We're running out of electricity and compute. It's not going to go on. So I think the deeper point to take away here is that something new has to come in, even if you want to work in regimes where you basically do have enormous sample sizes like LLM, something new is required. The other point to make here is that, there's many regimes where the brutal scaling is just impossible to begin with. By brutal scaling, I mean just collect more data, basically, and throw more compute. So here's an application, a kind of data where people do RL, but it's very, very different from sort of large-scale LLM type or deep learning type data. This is, I'm plotting as a function of the day that the stock market is open. There's roughly 250 days that a stock market is open. I'm plotting the log return of the index on the S&P 500 stocks. So what is the year that I'm plotting? It's for 1 year. Anyone have a clue? Roughly 20 trading days in a year. Something interesting happened around 50 days. That's roughly 2.5 months. You're looking late February, early March. Yeah, that's COVID, right? COVID produced some of the largest financial dislocations in markets since 1929. Okay? So that's obviously very extreme, but the deeper point here is that in data like this sort of exemplifies problems that many data poor regimes have. You don't have that many samples, and you can't just collect more. You have pretty limited data for the entire stock market. The stock market's not coming from some stationary system. It's not like, the system doesn't change. It's changing all the time. It's affected by pretty dramatic impacts, and it's, of course, affected by the way people behave. At some level here also you have the distinction between off-policy and on-policy data that I'll talk about later. If I'm an investor and I invest, an investment protocol is a policy. It's a way of allocating money. Those are actions you could take. And I could look retrospectively at how I did with some investment protocol. But what I really care about is a counterfactual. I care about if I did something different with my system, if I changed it in some way to a new policy, how would I do? That's the challenge of off-policy data that I'll talk about later in the talk. Okay, so those are sort of some broad observations, but I think it's sort of useful to keep in mind. I think in our current discussion of sort of data science, ML, and AI, we're kind of focused on a very particular kind of data and a very particular part of the space. The world is bigger and more interesting than that. So I want to sort of encourage us collectively to think about different problems. Okay, so in this talk, I'd like to give you two vignettes. I'll try and keep them not super technical, but they share this common theme of trying to develop methods that use data in more efficient ways. So the first part is going to be about a new method. I'll describe in a minute, but it's a way of performing policy evaluation, and it's a way of performing it when you collect data in an on-policy setting. You collect data using the policy that you want to understand the performance of. In the second part, I'll talk about off-policy challenges. This is a very big sort of general area, and what I sort of hope to convince you of is it's actually sort of, in some sense, more general than RL. It's connected to the problem of what's known as transfer learning or distribution shift, which I think is something quite generally important in ML for us to tackle and understand. Okay, so let's go back to our basic agent environment setting. All right, so we have an environment, we have an agent. Agents take action A, and we sort of imagine that this loop begins here in the left, that we begin in some state, in some action. The environment evolves in a random way. There's a transition function. We get a next state, I'll call it x prime, and a reward, I'll call it r. And then the agent has a policy. The agent is going to choose a next action a primed. Okay, so that's the basic loop, and we'll be studying that loop in detail. So pi will be a policy. That's how you choose to behave. All right, so ultimately what we want to do is we want to learn policies that are optimal or near optimal, things that when we run the policy for a certain length of time, we sort of maximize a notion of reward. Okay, so let's formalize that notion. Okay, so the value function of a policy, there's an equation here, but intuitively it's quite simple. It says, imagine that you ran the system according to some policy, you chose actions in a certain way, you run the system many rounds, you would get a sequence of rewards. What do those rewards mean? That depends on your application. In game playing, they could be things like points you receive or something like that. In control systems, they could be measures of quality of how well you're driving a car. Okay, so we have this trajectory of states and actions, and we have a trajectory of rewards. And what we sort of want to look at is, on average, how well do we do if we follow that policy? The other ingredient that we have here, just one sort of technical thing, but in the setting I'm looking at, you have a discount factor. This gamma is a number. It's between 0 and 1. And it basically says, how much do you discount the future? If that number is very close to 0, you're sort of saying there's not much value to things that lie in the future. Right now, inflation, or certainly last year, inflation was extremely high in this country. If you do any rational analysis of investing, you have to discount your money now, or money that you will earn next year or 10 years from now, by the inflation rate. It's simply worth less. So in general, that's something that one has to take into account. Other systems where rewards are very sparse, you might want to have very long memory, so you might actually want gamma to be very close to 1. That means you don't forget things, you have a very long memory. Okay, so there's sort of a range of behavior that we could have here. And what we're interested in is, the ultimate goal is to find policies that make this number big. or really this collection of numbers, big. So v pi is the value function. What I'm going to focus on here, RL is a huge area. There's a lot going on, a lot of different methods, a lot of sub-problems. I actually wanted to work on RL for a long, long time, partly because it has a little bit of everything. It has probability in it, has like Markov dynamics, it has statistics in it, it has optimization and algorithms in it, it actually has counterfactual inference in statistics, and it has a huge range of applications. But it's in some ways hard to get into. The literature can be a little daunting, to be frank. So let me just keep things very simple and concrete in this talk. And I'll focus just on a sub-problem. Okay, so the sub-problem I want to focus on, I won't talk about optimization. I'll just talk about the simple problem. I give you a policy. Pi is fixed. And you want to use data. You can collect data from the system. You want to use data to evaluate the value function. Okay, that's called policy evaluation. So let's focus on that problem. The reason I'm focusing on that is that's basically the core primitive. If you want to optimize, you have to be able to say, is this good where I am? And you have to be able to sort of suggest if I moved in this direction via something like a policy gradient method, would I get better? So basically computing values or derivative of value functions, this is really a core primitive in this area. Okay, so just a little bit of notation. Again, math aside, the intuition here is quite simple. What it says is if you look at the value function, it satisfies a simple fixed point equation that captures the following intuition. The intuition is my current value should be equal to my current reward. Right? So current reward. And then I have to take into account what happens in future. So I take into account what happens tomorrow. Tomorrow I observe a new sample x primed and a new policy, and I would sort of experience the value moving forward from that state. Right? And that's a random thing, so I take an expectation. Okay, so this is an operator, and it sort of tells you, gives you a way, in principle, of computing what the value function is. Okay? Now, in practice, we can't compute this operator. So where does data come in? If we think about this thing, that expectation there, that involves data. You're taking an expectation, involves some distribution. But I can draw samples to approximate that, a kind of Monte Carlo approximation. So the data in RL, what does it take? In a simple setting, it takes this form. You observe 4 numbers, or states and actions could be vectors. You have current states and actions. So in a state, you take an action, you get a next state, and you get a noisy reward. Okay, so you have quadruples of things, and you'd like to use those quadruples to try and approximately solve that operator equation. That's a fixed point equation. If your problem is simple, if it's tabular, if your states and actions are discrete, that's just a matrix equation, basically. It's just a linear system. But we're interested in the setting where your data is not tabular. If it's continuous, that's sort of what's called an integral operator equation. Okay, so that's the setup. Now, how do people use data to do this, and where does data efficiency come in? Okay, so if you're trying to solve a fixed point, one thing that you could do in principle is you could keep applying the operator repeatedly. So I could start with some guess, v1, and I could apply the Bellman operator in principle to get v2, and I could just keep powering it. So it's a power method or successive approximation. In reinforcement learning, that's called value iteration. That's not something you can implement, because as I said, you don't know the probability distribution, so you have to use data. So what do people do in practice? How do they use data? Let me tell you a standard way of using data, and then I'll tell you a better way of using data. Okay, so here's a standard way of using data. And it's useful because it's basically just saying I'm going to reduce everything to a giant prediction problem. Why is that useful? It's useful because we know how to solve a lot of prediction problems now, right? For certain classes of data, neural networks are state of the art. For other classes of data, things like boosting or random forests or kernels are state-of-the-art. Sort of depends on your class, but we have many methods that we could use to solve regression problems. Okay, so what's going on is you're using your data, you use it to construct a target. You're sort of rolling the Bellman equation out one. You're taking the reward plus a discounted version of what you currently think the value function is, and then you try and predict that. Okay, so you're just solving a big prediction problem. This script F that I have is generic. It could be a neural net, could be boosting, could be whatever you want. And that's, in some ways, that's the beauty of these methods, is they're sort of meta algorithms in some sense. You can plug in whatever you like. Okay, so how does that behave? These are the plots that you typically see. Okay, so what am I plotting? I'm plotting the number of iterations that you take versus, on a log scale, how quickly you converge your error goes to zero in estimating the value function. So I'm plotting two things. The pentagons in red are actually the data-based approach, and the green squares are the oracle. You cannot implement this in general for a real problem, because that assumes you know all the transitions. But that's just to compare. What's relevant here is you see that these plots are linear on a log scale. Okay, so that means you're seeing geometric convergence. The algorithm is converging sort of basically as a function of gamma. It's reducing the error as a function of gamma. And that's not surprising, because if you look at this, the Bellman update, remember gamma is less than 1. So this algorithm is contracting. It's pulling points closer together every round. What you see is you lose something with using data. Fitted value iteration is slower, but you can see it's geometrically convergent. Okay, so what I'll show you today is a new algorithm that, on the same problem with the same data, produces these plots. What is it doing? It's solving prediction problems, but it's actually solving them for a very different reason. It's not trying to approximate the Bellman operator. It's trying to grow a feature set, and I'll explain how that works. And what's interesting is you can see it's much more rapidly convergent. After maybe 10 steps, you're getting error that's quite small. And you can also see an error floor. There's an error floor because you're using data. There's a finite precision because you have a finite number of samples. Okay, so why is this an example of data saving? Well, remember, every single point on this curve involves solving a prediction problem. And that prediction problem in general could be quite large scale. It might take minutes, it might take hours, who knows? It depends on the structure of your problem. So if I give you a procedure that takes roughly 10 iterations to get tolerable error, you're going to save a lot of data. You can stop much earlier. To be fair, this example is quite hard because the discount factor is very close to 1. But it is representative of more general behavior that we see for this algorithm. So any questions so far before I give you a little intuition for what's going on under the hood? Yes? So I'm not going to talk too much about theory. We have theory, but to be honest, the theory has not caught up to practice, which happens. I can tell you why there's an error floor. I can give you rough predictions. The error floor is happening because you have a finite number of samples that you're solving the predictions with. So the algorithm converges quite rapidly. We can predict that, and we do predict that there should be an error floor. The reason I got two curves here is, for one, I used probably sample size 10 times larger than the other. In practice, what you should probably do is use a small sample size initially, and then blank the screen, and then refine it as you go. So, okay, so let me just try and give you some intuition what's going on, because it's actually relatively simple. Okay, what it's doing is at every round it's constructing a linear approximation to the value function. Okay, so that sounds totally crazy. Linear representations are somehow very weak. But it's doing this in an adaptive way. you can be linear in features that are actually very nonlinear. And so the whole system is actually very nonlinear. And it's adaptively nonlinear. It's choosing the features in a particular way so they're most efficient at approximating the value function that you're after. Okay, so there's sort of two ingredients, and I'll unpack them for you in sequence. The first is, how do you compute a best approximation at round t? Okay, at round t, we're going to be given a set of t features, and I want you to figure out how to construct weights that are best within that class for approximating the value function. The answer to that is straightforward. It's not new. You use something called least squares temporal difference, and I'll give you intuition for what that's doing. The second question, and this is where the prediction comes in, is how do you actually find the best new feature to add? What we're essentially doing is a form of boosting. Boosting is just a fancy way for saying you construct predictors by fitting the errors that you make. You have a current prediction, you fit the error and use the error to adjust your prediction. So we're just boosting. So at some level, these two ingredients are not really new. People know about the connection in the tabular case in the sort of more classic DP setting between LSTD and Krylov. And people have proposed that you might boost for policy evaluation. What's new is the way in which we interleave these things. Both ingredients are critical. You can't just do one. It doesn't really improve things if you only do one. Okay, so we call this Krylov-Bellman boosting. Bellman because it's trying to solve the Bellman equation. Krylov because it actually has connections to methods in numerical analysis called Krylov methods. Okay, so let me just give you a little bit of geometry. There's a few equations here, but essentially all the intuition is in the geometry. So let me give that to you. Okay, so imagine that we have a set of features. We'd like to approximate things. So what do? We try and estimate some weights that I'll call omega, and we put them in front of our features. Okay? How should I estimate those weights? This is not a regression problem. This is a fixed point finding problem. So what I should do is something that actually people have been doing to solve PDEs for well over 100 years, something called a Galerkin method. What is a Galerkin method? It's a fancy way of saying, let's do the following. Okay, so you have a linear subspace, right? You're representing things by linear combinations with weights. That's something flat. You can sort of imagine the following, that I might start with something in my linear subspace G, and if I apply the Bellman operator, it's going to take me very nonlinear right away. I won't be linear in those features unless it's something called a linear MDP, or I guess a low-rank MDP. But you can imagine I could project back onto the subspace to sort of get myself back to the class I care about. The point that we're finding is very special. It's the point that if you start there, this F star, you start in the class, you apply the Bellman operator, you unroll the dynamics of the MDP, and you project back, you end up exactly where you started. Right? So it's sort of a certain self-consistency condition. I have an approximation, I apply the Bellman update to it, it gets out of my approximating class, I project back, I get exactly where I started. Okay? That's the point that we're computing. It's called, in the context of RL, it's called the LSTD fixed point. Okay? So operationally, that gives you a set of weights. If you have D features, it gives you D numbers. It tells you how to combine your features. And sort of what's key here, and this informs what you boost on, is from undergrad linear algebra, this is sort of linear algebra in a Hilbert space, but you know that if you project things, the error becomes orthogonal. Okay? So the error that you're currently making is orthogonal to your current set of features. That's a very good direction to try and add to your feature set. It's sort of where you're changing in the worst possible way. So what are we going to do? We're going to boost, we're going to fit your current error. We're not going to fit the Bellman function, we're going to fit the error in the Bellman function. Okay, so that's the second ingredient. You boost on the residual. But details aside, really the only difference is the way you construct your responses, what you fit to, you don't fit to the Bellman updates, you fit to the error, your current error in the Bellman updates. Okay, so the computational complexity is exactly the same as the original problem, but the target's very different. And then the overall algorithm is just doing that in sequence. The first step is a linear system solve. The second step is whatever prediction you use. If it's a deep net, it's a deep net fit. If it's a kernel, it's a kernel fit. And we're just interleaving that and adaptively growing the subspace. That's the algorithm that generates these plots. So any questions about that setup? Sort of details aside, I think sort of intuitively it's a very reasonable thing to do. You know, whenever you use linear approximations, the question you would ask is, well, where did you choose the functions that form the basis? And this is just saying, well, don't choose them up front. Let your data tell you what they should be based on what the error in your current evaluation is. So it makes a fair bit of sense. We can prove some things about it, but I think just to keep things less technical here, I'll defer that. Happy to talk with anyone who's interested offline, but this can lead to some pretty big savings in different problems. This is a problem where you see roughly a five-fold saving over fitted value iteration in terms of how much data you have to collect. This is a problem where the tolerance is sort of medium. You're not getting very accurate answers. If you want more accurate answers, quite fine answers, you can see much larger savings by using this kind of procedure. Okay, so what you should take away from this is to implement this, it's not very hard. It's a linear system solve plus plug into whatever your favorite prediction routine is. Do that recursively, and you'll generate plots that look like this. There's some interesting things, other things to talk about with this algorithm, but I think just to keep us on time, I'm happy to come back to these plots and discuss if there are questions. All right, so let me segue a little bit, just so you're sort of clear that the model that I was talking about just now is sometimes what's called the generative model of reinforcement learning. It sort of assumes that you can fix a state in an action, and you can run the system, get rewards and next states, and you can do that however you like. It's not really adaptive. I'm not allowing you to do explore-exploit trade-offs, so that's perhaps something that you can do. It really depends on your mechanism for collecting data. In the second part of the talk, I want to talk about something that is, in practice, really important. Tons of work in this area, but lots of open questions. In practice, it's often very difficult to collect new samples. If collecting a new sample involves simulating a high-dimensional system, as I said before, that can take hours or days. But it's possible that many other people have collected a lot of data for you. And it's been logged. It's sitting somewhere on some servers. This data is called off-policy data, because it wasn't collected according to you, according to what policy you'd like to evaluate. It's collecting maybe not even according to any policy. You have no idea. So think self-driving cars. You might have some new idea about how to have a policy for self-driving cars. You might want to experiment with it. You're not going to just roll it out in the real world. But there's enormous data sets. For instance, I was just hearing about them from Waymo that have a ton of self-driving car data. Okay, so that's available to us, very, very large, what are called off-policy data sets. So there are really two motivations here. One is we, in some cases, have very large pre-collected data sets. Self-driving cars is an example. Robotics, people have done lots of simulations. Say I'm a doctor, oncology treatment protocols, many people have had cancer. We've applied certain sequences of treatments to them. So how do you use that data effectively? The other case is, sometimes it's basically impossible to collect on-policy data. It might be unethical. If I have medical treatments, if I discover one thing is actually effective, it's perhaps unethical to use things that I know are less effective on patients. It violates the Hippocratic Oath. If I have drug treatments, I can't just have some crazy idea of drug treatments and randomly apply them to people. That's also unethical. Another example is in economics, banking, and finance. People use sequential routines, RL, to try and make decisions about how to give loans to people. Okay, so here the features are things, variables about a customer, their salary, their employment history, their bank records. Actions are, binary. Do I give a loan or not? What are the terms of the loan? How much? What's the interest rate? These are all things that I can control. And the reward is pretty obvious. If loans default, you lose money. If loans don't default, then you recoup the interest payments and ultimately the principal. Okay? So here, a bank cannot just say, I have a new policy for assigning loans. Let me just randomly run it. They could do that. There's nothing unethical per se, but they'll lose a lot of money. If the policy is bad, they'll make a lot of bad loans, and they'd lose a lot of money. The other thing the bank has to worry about is what's called adverse selection. If they run a certain policy and it's too lenient, people will game the system. They'll figure out, this bank has very lenient terms, and it actually affects, there's sort of an interaction between the action and in this case, the distribution of the customers, the states. It will entice people with low credit scores to enter the system. Okay, so this is another setting where really you have to think about using off-policy data. On-policy data is either impossible or it's scarce. Okay. So what's going on here, if we sort of formalize a little bit, as I mentioned at the beginning of this talk, this is really a particular case of the more general problem of sort of distribution shift in statistics and machine learning. What I mean by distribution shift is you have two distributions, one under which you collect data, and another under which you want to have good performance. Okay, and this shift, that these two distributions are not equal, that's the typical assumption when we make an ML, is that training and test data is the same thing. That condition is violated in these examples. Okay, so in this RL application, what's going on? Your source, I'll call it P, is a big offline data set. You've collected a lot of things. They might have been according to a policy. I'm sort of writing that here, but they might have been according, who knows, a mixture of policies or maybe no policy at all. And you might not know what it is. But you do have a target, and that target's very well defined. You have some policy, I'll call it tau, for target that you'd like to evaluate. You want to know how good that policy is. Okay? And so this has a new ingredient, something we didn't see before. Before, the data that I collected in the first part of the talk, that was on policy. It was from the policy that I cared about. This is a new ingredient. There's now this shift, a mismatch between the data that you have and the policy that you want to evaluate. Okay. All right, so how might you formalize this? People study this problem a lot, and sort of intuitively, what's the issue? The issue is that if you think about the ratio of these two distributions, the target to the source, what are you concerned about? You're concerned about if the offline data, the source data, has very bad coverage in certain regions of space. If you see very few samples or possibly no samples, then it's going to be very hard to evaluate how you would do in the counterfactual world of the target policy. Okay, so that discrepancy, you can measure it by looking at the importance ratio between the target data, I'll call that Q, and the source data P. Just to be clear, even writing that, that's an assumption. It's an assumption that that thing exists. I'm going to give you theory that doesn't require it to exist. It's possible that you're zero at some points in the source and non-zero in the target. Okay, so that's an importance ratio. What do people do? This is a very active area. I can't sort of do full justice to it, but there's sort of, both in regression and specifically in reinforcement learning, there's sort of different classes. Some people assume that they know the importance ratio. That may or may not be realistic. Sometimes I do, sometimes I don't. And if I knew it, then I can basically reweight all my samples. If I multiply my samples by this ratio, then what are you doing? You're sort of converting every P sample into a Q sample on average. That's what importance weighting does. It's just reweighting to make your samples have the right kind of coverage. But you can see that could be very bad. If this ratio is very large, multiplying something by a large number is going to make it fluctuate a lot. It will have very bad properties. Other people put constraints on the importance ratio. You might assume that it's uniformly bounded. This, in RL, leads to what are known as concentrability coefficients. Okay, so I don't want to do these things. Let me tell you what I'd like to do. I'd like a measure that can handle this problem. Okay, so this is a problem where your source sort of gives you mass between 0 and it looks like 0.3 and maybe 0.7 to 1, but you have no mass in the middle. So you never see this, think of these as states or actions, you never see actions in the middle. If your target is uniform like this, then that importance ratio doesn't exist. Okay, so you can't do importance rating, you'd be multiplying by infinity. It doesn't make sense, but we should be able to handle this. And why is that? Well, what do we really care about? What are we trying to do? We're trying to estimate value functions. And to estimate value functions, you approximate them somehow. You use a function class. And so anything that we do should sort of depend on how complex that function class is. If you had a linear function class, what's the game that we're playing? If you're an adversary, right, what would an adversary do? They would try and hide a function that has a lot of mass where you don't see anything under the source. If you never see these points, you can't estimate anything about this. And you would pay a price because the target does put mass on those points. But how well you can hide functions depends on how complex the functions are. If you only have linear functions, you can't really hide much. You can make it 0 everywhere, but then it's not an interesting function. Any linear function that you do is going to have non-trivial mass in these blue regions in parts of the space that you do see. Okay, so linear functions should be easy. Other functions, if I allow you more freedom, I can start building bumps or little crazy things. I can make functions that put almost all of their mass in the unseen part of the space that you never saw in the training data. Okay, so those are going to be bad functions in some sense. Okay, so what we measure is we have two distributions. We can measure weighted norms either under the target or source, and we look at the ratio of the two norms. How bad can that ratio be? So that ratio depends on the source and target, but also depends on the functions. You can compute this ratio for some examples. Let me give you some examples. If you have sort of simple functions that are differentiable, and you sort of ramp up over a sequence of problems, changing the gap, we have a ratio, I'm calling it B. When you have no gap, there's no source target defect, you get B is 1. As you increase that number, it grows. Okay, so that number is going to grow. And how it grows, this is just a simple one-dimensional example, but in high dimensions, it's going to grow in different ways. How that grows is what sort of matters for the performance of methods that are dealing with covariate shift. Okay, so I do have a theorem. I think probably I'll keep things light, but again, I'm happy to get more technical for those of you who are interested afterwards. Let me just, to wrap up, let me just show you an interesting empirical phenomenon that our theory is meant to explain. Okay, so what we're doing here is a very simple regression problem. There's nothing in our theory about 1D problems, but I'm just choosing this to illustrate. What am I plotting? I'm solving a regression problem, and I have a regularizer that's enforcing a kind of smoothness on the problem. And as I increase this number rho, I'm sort of penalizing smoothness. I'm making you smoother and smoother. And I'm plotting the value of that regularizer versus the accuracy of your prediction. On the y-axis, we have prediction accuracy. And so this is just a standard bias variance trade-off. There's nothing at all exciting going on here. What is exciting is when I introduce covariate shift to the problem. These are the plots that you see. Okay, so each one of these curves corresponds to a different amount of covariate shift. The red dashed is covariate shift 5. That ratio is 5, 10, and 15. Okay, so what's happening? As you have more mismatch between the target and the source, you get worse. Okay, all these curves shift up. That's not surprising. What is interesting and is more subtle is what is the optimal choice of regularization parameter? That's this minimum here. And what's happening as you increase the amount of mismatch? It's shifting to the left. Okay, so for some reason, you should regularize less if you have worse mismatch. Okay, so why is that happening? Is that just specific to this example? Is there something more general going on here? Okay, it's sort of saying that you should under-regularize as a function of how much mismatch that you have. Okay, so we have some theory that explains this. I think in the interest of time, I won't go into this in detail, but let me just sort of convey to you why is that shift happening? That shift is happening because, at least in a worst case, you have to deal with the following phenomenon. Okay, so if you're an adversary, what can you do to make the problem very hard? So imagine that you're dealing with functions that, let's say at some particular state in action, they always take the value 0. There are many classes that satisfy that, but just as a thought experiment, imagine that's true. Why is that interesting? It's interesting because if I ever have state action that are equal to x0, a0, it's completely uninformative to me. I already know that the value function is 0 there, so those samples tell me nothing. Okay, so what should an adversary do? An adversary, if it's evil, should exploit this fact. It should put a lot of its mass at those totally uninformative samples. And by doing that, it basically makes it so that almost all of your data is totally irrelevant. Okay, the only samples that are relevant are the ones that come from Q. That's your original target. We're sort of assuming that the source is a lot of data at one point that's totally uninformative. And some data, remember B is bigger than 1, B can be large, some data that's coming from what you really care about. Okay, and if you do that, it's basically like you have a problem with a much smaller sample size. Your adversary has sort of made it so that a lot of your data is useless. You may as well throw it out. And if you work through the calculations of how you should do bias variance trade-offs in this example, it says that you should under-regularize. Okay, so that's in a worst case, and that explains these plots. We have more general theory here. I'm happy to discuss this in more detail, but I think let's just sort of keep it light for this audience. Just high level, this is a theorem that says very precisely as a function of this mismatch between the two distributions for a certain class of prediction methods, what is the optimal thing to do and how much larger does your prediction error get? So this theory explains that particular phenomenon I just said, but it also explains a number of other things that I think are interesting. All right, so let me just wrap up. So I sort of began by arguing that, as in Donahoe's words, that the brutal scaling of throwing more data and more compute at things will not last forever. In the words of Stein, he's an economist. He's talking about other things, but he said, that which cannot go on forever will stop. I think that's sort of apt here. But aside from that, aside from very large data regimes, I think there are plenty of regimes where we're really small or medium data, just because it's difficult or expensive to collect things. And I think in this regime, there's a fair bit of opportunity for new algorithmic insights. I think we need new ideas here because we don't have the easy answers of just more data. One thing that, let me just sort of wrap up by saying something that I didn't talk about, but is actually very important for making these methods ultimately practical. Let me just finish with this, is if we look at this example here, we can see the blue curve, the Krylov-Bellman, is very rapidly getting very low error. And so that's sort of theoretically interesting, but that's totally practically useless because these are not curves that you can actually compute without knowing ground truth. So the open problem, and something we have partial answers to, are can you actually use data to effectively predict how rapidly your error goes below some threshold? For this example, I might be perfectly happy after maybe 3 iterations to stop because I'd get something like 10 to the minus 4 error. And what's important is this depends on the problem. Some problems are easier than others. Some problems you need a lot more iterations. But if you want to make these things practical, you sort of have to figure out how to use data to actually predict error. And you don't want to use holdout data here. That's wasteful and expensive. You want to do it in a purely in-sample data-dependent way. So that's something that we're thinking about and have some ideas. Okay, so yeah, wrapping up. I think there are lots of interesting questions in this general regime. As I mentioned, sort of an area that has lots of applications, but I think it requires new ideas. So thanks very much.
Thank you so much for the great talk. Questions?
Need an icebreaker.
Really interested about the covariate shift presented in the second half. It seemed as though those results are not specific to RL applications, and they could be more broad. Or is
That is correct. At some level, it's related to RL in that RL uses prediction to solve subproblems, but our sort of framing and analysis is not really RL specific. Yeah, I kind of think this covariate shift, arguably, in statistics we like to say training and test, and they're both IID in the same distribution. I would say it's more often violated than not in sort of modern practice of ML. So there's a whole workshop at the Simons Institute at Berkeley next semester that I was partly involved in co-organizing, all about distribution shift, transfer learning, things like this. So I think it's quite topical and important for us to think about.
I have a follow-up question on that. Intuitively, does that mean that we want to use less regularization such that we make sure that we learn the other, I think there were 2 parts in the graph, the minority part too, like both sides of the distribution very well, such that we can use the smaller part for the shift of data?
To be honest, this is a very toy example. So I don't think we should infer too much from this, other than it's the simplest example where there's, the likelihood ratio doesn't exist, right? There's really zero coverage. This little vignette that I gave you is actually what is going on. And this has nothing to do with, the theorem I gave is for kernels, it's specific to kernels, and it has nothing to do with any of that. There's no method for covariate shift that can, this is sort of a lower bound. You can see you could prove a lower bound for this. So in the worst case, no method can overcome this problem. But that's the problem with lower bounds. If somebody says a lower bound, you should always look at their construction, because lower bounds are often very weird and adversarial. And this is very weird and adversarial. Your adversary is saying, oh, I'm going to put all my points here, and I know exactly what's going on. What one actually needs, and we have some of this, is you need sort of a general theory that says for general P and Q, not a worst case P and Q, what should you do? And the answer is more subtle. You don't always under-regularize. You do something else. And we have some understanding of that, but it's not complete. Yeah, but this under-regularization, there's actually lots of work on high-dimensional ridge regression and I guess on some other aspects of kernels where people argue for under-regularization. Some people actually argue for negative regularization, but I think the settings in which that's actually good are pretty artificial, in my opinion. It's not a sort of generic property.
So there is the assumption, there's any assumption on F? Or?
Okay, so I didn't talk about this theorem, but this theorem is for kernels, so any kernel. We're assuming that F, it's well specified, so the function you're estimating is in the kernel class. And we're telling you how well can you do and what is the best procedure. And the best procedure is, in a worst case, something that minimizes this bias variance trade-off. Right? You minimize, you choose rho, that's the regularizer, to minimize these two terms, and you just do a simple regression with that weight. Now, to be fair, that's not practical because you don't know these things. But there's some nice follow-up work by Kai Zheng that proves you can actually use data and pseudo-labeling to construct a procedure that figures out this optimal rho without any knowledge. We weren't assuming any knowledge of Q. He just assumes you have unlabeled samples from Q, from the target. You pseudo-label them and do some clever stuff, and he gets this result up to a log factor. So that is actually a practical result. But it is a bit worse case. So that's a great question.
So you motivated the second subset of the work with off-policy data, right?
Yes.
But I guess the final result is that we should not regularize too much. So how is that concretely helping us to make use of this off-policy data?
Yeah, so there's a much bigger story here that I'm not sort of getting into. You're correct that the concrete conclusion of what I said in this part of the space is that in a worst case, you should under-smooth. So if you're doing sort of fitted value iteration or you're doing something like Krylov-Bellman, anything that's using repeated off-policy predictions, in a worst case, it's good to under-smooth. I think the story is far more subtle because that's a worst case statement. What one should actually do in RL is be looking at the structure of P and Q, the behavioral policy and the target policy, and one needs more refined versions of this. The answer is not just to under-regularize. The answer is to construct a different regularizer that's more complicated that depends on the two distributions.
So the assumption here is that you know what data is off-policy data, right?
The assumption in my work actually is I just have off-policy data. I don't know the off-policy distribution. I know very little. As you start to add more things, then I can start to say stronger things. But in the setup that I gave, I'm actually assuming essentially little knowledge of the problem. In the RL setting, I think it starts to become realistic to assume more things. It's pretty realistic to assume you know the target policy, for example. Whether you know the true source distribution of the behavioral policy, that seems unrealistic to me. So I think it depends.
Thanks.
Last question.
You need your magic finger again. You have to cut it off.
Yes,
So
exactly.
just one more question, because when you compare the Krylov space method versus, for example, the power method, there's acceleration.
Yes.
It's like natural momentum versus gradient descent. So in your method, the so-called Krylov-Bellman method, were you also able to prove the accelerated rate compared to the fitted Q-learning?
We can. There's a backup slide that has a theorem, but I can tell you sort of reasons why it's not totally satisfying. what we sort of prove is that at every round, I mean, Krylov methods are kind of fitting the spectrum. And we prove that at every round it's sort of growing things and it's reducing portions of the spectrum in a particular way. And we can prove a bound. Yeah, I mean, details aside, the first part is a contractive term, but it depends on spectral quantities that are actually being reshaped iteration by iteration. So that's what we can prove. It's a one-step bound that says you reduce, but with a contraction factor that can get faster and faster as the algorithm grows. It's kind of what you expect from a Krylov method because it's sort of fitting all the eigenspectrum, and if it fits it well, you're going to do better. But this is deficient. This doesn't, if I simulated and used this as an upper bound on the behavior of the method is far better than that theory says. So it's qualitative, I would say.
So can I understand that for the standard fit Q-learning, you probably don't have this square in alpha t or something like that?
Standard fitted Q would be very easy to show that you get contraction like this with 1 minus gamma.
1 minus gamma. Oh,
Gamma is the discount. So if, so if the discount was 0.99, you get contraction with a factor 0.01. That's almost, it's very, very slow. Both algorithms will have, statistical error because you're using samples, but that can be controlled by how many samples you use in each of the fits.
And here, alpha t and beta t may also depend on gamma in certain way.
They do, because the spectrum depends on the transition operator of the MDP weighted by gamma. So if gamma is smaller, that's good, but this method adapts to all the eigenstructure in the transition function of the MDP. So yeah, we have some understanding, but yeah, just to be full disclosure, it's not fully satisfying.
Thank you.
Yeah.